Okay, so we have a condensed matter physics practice final exam. So let's begin. Number one, consider a two-dimensional crystal and primitive lattice vectors given here. A sub 1, and then it's A, 1, 0, A sub 2, A, 1 half root 3 over 2, which forms a triangular. Some people would call this a Bravais lattice, some Bravais. Some call it Bravais. Pronunciation varies. Okay, so for part A, we want to derive the reciprocal lattice primitive vectors B sub 1, B sub 2. Describe the Brillouin zone. Determine the area of the first Brillouin zone. Also, a free electron in this lattice has a wave vector located at the corner K point of the Brillouin zone. Pardon my French, I don't speak French well. Pardon me if I mispronounce anything. Determine the corresponding free electron energy. Okay, so let's begin with the reciprocal lattice and Brillouin zones. We're given A sub 1 and A sub 2. I'm gonna go over this very quickly so you have this as a reference. I'm gonna skip some steps. There's some intermediary steps that are skipped, but this is basically that gives you the setups and segues into steps and whatnot in the solution. So we'll do this quickly so you have a reference if you want to try the problems. Okay, and check. All right, so a unit cell area is, if we take the cross product of the vectors and their magnitude, we get square root of 3 over 2a squared. Reciprocal lattice vectors that satisfy a sub I dot b sub j, that gives you that 2 pi delta ij sub ij, and I apologize, my deltas are very poorly drawn. Solving for b sub 1, b sub 2, we get the following two. 2 pi over a, 1, negative 1 over root 3 for b sub 1, and 2 pi over a, 0, 2 over root 3 for b sub 2. The first Brillouin zone is a regular hexagon. Its area here, area of the Brillouin zone, is 2 pi squared over a, 4 pi squared over root 3 over 2a squared, and we're going to get 8 pi squared over root 3a squared. For a triangular lattice, the distance to a k point is the magnitude of k, and that comes out to 4 pi over 3a, and thus the free electron energy, that would be E sub k equals h bar squared, k squared over 2m equals h bar squared over 2m, 4 pi over 3a squared, and E sub k is 8 pi squared h bar squared over 9ma squared. And pardon me if I mispronounce anything, I apologize for that. That's number one. Moving along to number two. Okay, so we have number two here. Okay, so number two, one-dimensional crystal has lattice spacing A and weak periodic potential V of x equals 2 V sub g cosine gx, cosine of g of x, g equals 2 pi over a. Okay, I'm going to just read this out, A, B, C, and D. Using degenerate perturbation theory, derive the energy splitting at the Brillouin zone boundary, show explicitly that a band gap opens, and compute effective mass near the bottom of the lower band to leading order in V sub g, and discuss physically why electron group velocity vanishes at the zone edge. Okay, so nearly free electron model, we're given the potential here. At the boundary zone, k is g over 2, equals pi over a. We have this, this states this k ket and this k minus g ket are degenerate because of the following, that E sub k superscript 0 is equal to h bar squared k squared over 2m, and E sub k minus g superscript 0 is equal to h bar squared k quantity k minus g squared over 2m. And at k equals g over 2, k minus g quantity squared equals negative g over 2 squared equals g squared over 4. So we get the perturbation matrix here. and the eigenvalues are over here. Okay, so therefore the gap is going to be delta E equals twice the value of the magnitude of V sub G. And we could say that the band gap opens because the periodic potential mixes the right moving and left moving electron waves at the zone boundary, forming standing waves with different charge densities relative to the ionic lattice. Near K equals 0, the nearly free electron energy is given as this E of K function. Okay, and expanding for small k, we get E of K approximates this function here. All right, some of the stuff I'm not going to say because it's right there for you. E sub G equals this, and then we thus have our h bar squared over Tm star equals the h bar squared over 2m minus 8 magnitude of V sub G squared over E sub G, G squared. And we could say that the group velocity vanishes at the zone edge because V sub G equals 1 over h bar d dk, and the band flattens at the boundary. Okay, so moving forward here for number 3. Okay, I'm probably going to go through this rather quickly, this practice exam. Consider a one-dimensional diatomic lattice with alternating masses m and m connected by the springs of constant k. Derive the equations of motion. Obtain the dispersion relation for both acoustic and optical branches. C. Show that the acoustic branch becomes linear for k is approaching 0. Determine the optical photon frequency at k equals 0. And E. Explain physically why optical phonons that is, can interact strongly with electromagnetic radiation. So phonons in a diatomic chain, let U sub n be displacement of mass m and V sub n of mass m. The equations of motion are given here. Okay, and assume these wave solutions for U sub n and V sub n. Substitution gives this dispersion relation here. This is canonical, okay, for omega squared equals this. The minus sign gives the acoustic branch, the plus sign gives the optical branch, and for small k, we get the following. Sine of Ka over 2, that's going to approximate K over 2. And the acoustic branch becomes omega equals V sub s magnitude of K, so it is linear near K equals 0. Okay, and then the optical branch at K equals 0, omega squared equals this quantity, so we wind up with this omega sub OP of 0 equals that square root of 2k times quantity 1 over m plus 1 over m. And we could say optical phonons couple strongly to electromagnetic radiation when opposite charges in the unit cell move out of phase, producing an oscillating electric dipole. Okay, so that's the setup for number 3. Let's go for the setup for number 4, problem 4. Okay, using the Debye approximation in 3 dimensions, derive the density of phonon states, G of omega, derive the Debye specific heat formula, show that at low temperature C sub V is proportional to T cubed. My apologies for that horribly drawn proportional symbol. And estimate for letter D the Debye temperature for material, where sound velocity is given as 4.5 times 10 to the 3rd meters per second, and atomic density is 8 times 10 to the 28th meters per meters cubed. Okay, so the Debye model of specific heat for photons in 3D, we get omega is V sub sk. Number of modes inside the sphere, radius k is n of k equals that value here. Okay, so n of k is going to be vk cubed over 2 pi squared, and using k is omega over v sub s, we get the following for n of omega. K equal, so here, k is omega over v sub s. Here's the n over n of omega formula here. So g of omega, that equals the derivative of n with respect to omega, dn d omega, equals 3v omega squared over 2 pi squared v sub s cubed. The internal energy is going to be this integral, u equals from 0 to omega naught, h bar w times that quantity 1 over e to the h bar omega over k sub bt, and then minus 1 G of W dW. Then our C sub V is du dt partial at low temperature. C sub V is proportional to T cubed, and we get this for C sub V, 12 pi to the fourth over 5 nk sub B T over theta sub D cubed. That being our Debye temperature. Okay. So, moving along here for the numerical estimate, K sub D is 6 pi squared n to the 1/3, with n is 8 times 10 to the 28th, m to the negative 3. And K sub D is 1.68 times 10 to the 10th, m to negative 1 when we do the computation. Again, I skipped a bunch of intermediary steps. So the Debye temperature is this H bar V sub S K sub D over K sub B. And we're going to use here V sub S. Should look familiar, 4.5 times 10 cubed meters per second. And here we get the Debye temperature, 580 K. Okay, so that takes care of the setup for number 4. Problem 4 setup. Problem 5. Okay, consider a three-dimensional free electron gas. Derive the density of the states G of E. Part B, show that the Fermi energy at T equals 0 is E sub F equals H bar squared over 2m times the quantity 3 pi squared n to the 2/3. Part C, show the low temperature electronic contribution to the heat capacity. And part D, explain why only electrons near the Fermi surface contribute thermally. Okay, so Fermi gas and density of states problem. So for the 3D electron gas, we're going to use E equals H bar squared K squared over 2m. That's the number of states up to K, including spin, is going to be this N of K equals 2 times V over 2 pi cubed, 4 pi K cubed over 3. So N of K is going to become VK cubed over 3 pi squared. So N of V is going to be V over 3 pi squared times this quantity when we substitute for K. And therefore G of V is dN dE. And G of V is going to be that V over 2 pi squared, 2m over H bar squared to the 3/2 times E to the 1/2. And at T equals 0, N equals N over V. That equals K sub F cubed over 3 pi squared. So K sub F is 3 pi squared N to the 1/3. So E sub F gives us H bar squared over 2m times the quantity 3 pi squared N to the 2/3. And at low temperature, we have C sub V. That equals gamma T. And with gamma, that equals pi squared over 3 K sub B squared G of E sub F. And we could add here at the end, only electrons near the Fermi surface contribute because states deep below E sub F are filled and cannot absorb small thermal energies due to the Pauli exclusion principle. So that's the setup answers as well for number 5. Let's move along to number 6. Oops. Sorry about that. Okay, number 6. We have BT and band structure. So state improve bloke. Some call him bloch. Some call him block. Bloch, block. All I've heard it pronounced all different ways. Again, I'm not a language specialist. So if I'm not giving the preferred pronunciation you've heard, my apologies. I've heard the name pronounced different ways over the years. So, for an electron in a periodic potential, show how crystal momentum differs from ordinary momentum. Explain why electronic states may be labeled by wave vector k within the first BZ, and a semiconductor has a direct band gap. Explain experimentally observable consequences compared with an indirect gap semiconductor. Okay, so for a periodic potential, V of R plus capital R is V of R, and the Hamiltonian commutes with the lattice translations H T sub R equals 0, and therefore eigenstates of H can also be chosen as eigenstates of T sub R. So we get this for T sub R, psi of R equals that. And then psi sub k of R equals this expression, where U sub k, R plus capital R equals U sub k of R. So this is more canonical stuff. We could say here the crystal momentum differs from ordinary momentum because ordinary momentum is not generally conserved in a periodic potential. Instead, momentum is conserved module a reciprocal lattice vector, K similar to K plus G. Therefore, all states may be labeled with the first BZ. A direct gap semiconductor right here allows vertical optional transitions in K-space, so photon absorption and emission are efficient. An indirect gap semiconductor requires a phonon to conserve crystal momentum, so optical emission is weaker. Okay, so that's a phonon. Moving along now, that's for number 6. Let's move to number 7. Okay, so number 7. Okay, so we have here a semiconductor has conduction band edge E sub C, valence band E sub V, and intrinsic carrier density N sub I. Here are A, B, C, and D. Derive the expressions for the electron and hole concentrations. Show that NP equals N squared. Determine how the Fermi level shifts in an N-type semiconductor with donor concentration N sub D. Explain why semiconductor conductivity increases with temperature while metallic conductivity generally decreases. So semiconductor statistics for a conduction band, N equals that integral from E to C to infinity, G sub C of E, F of E, dE. In the non-degenerate limit, N equals this. Okay, and here what we have for holes, we have this equation for our holes, and this gives this equation here. Now multiplying here NP equals N sub C, N sub V, E to the negative quantity E sub C minus E sub V over K sub B T. And since EG equals this, we could get NP equals the following expression, just doing the computation here. Okay, so let's see here. That's for an N-type semiconductor with donor concentration N sub D. Let's see, assuming full ionization, N approximates N sub D, then N sub D equals this. Okay. All right. And solving for that, we get E sub F equals this quantity. All right. So I skipped a lot of the intermediary steps with the computation. And then here, and just led to the answers. I'm sure you could do that. I'm sure you could do, a lot of you could do a lot of this whole exam yourself, especially if you're really into physics and you enjoy this stuff. This is just extra practice again. So in part D, semiconductor conductivity increases with temperature because work carriers are thermally excited, and metallic conductivity generally decreases because increased phonon scattering reduces mobility. Okay, so that's for number 7, and let's move along to number 8. And hopefully I said phonon and not photon. Phonon scattering. Sorry about that. My apologies if I miscommunicate. Number 8, consider the two-dimensional Ising Hamiltonian. H equals the following. Explain the physical meaning of ferromagnetic versus antiferromagnetic coupling. Part B, use mean field theory, derive the self-consistency equation for the magnetization, determine the critical temperature T sub C and the mean field approximation, explain why fluctuations become important near the phase transition, and letter E, discuss the concept of spontaneous symmetry breaking in this system. Okay, so here's the Hamiltonian. If J is greater than 0, this is canonical textbook type stuff here. Important though, very important. J is greater than 0, a line spins lower the energy, so the system is ferromagnetic. If J is less than 0, anti-aligned neighboring spins lower the energy, so the system is anti-ferromagnetic. Okay, moving to B. In the mean field theory, each spin feels an average field from its neighbors. Okay, here what we have with the summation here for S sub j, and going to equals the m, where z is the coordination number, and the effective energy of this spin is E equals this negative j z m s. Thus, you have that m equals that average value of s. Okay, notation equals the following: that e sub e to beta jzm minus e to the negative beta jzm over e to the beta jzm plus e to the negative beta jzm. Okay, and then therefore here our m equals that hyperbolic tangent of notation of beta jzm. Okay. Near the transition, m is small, so we get this is approximately beta j zm. A non-zero solution requires this: 1 equals beta sub c jz. Therefore, k sub b t sub c equals jz, or t sub c isolated is j sub z over k sub b. Here, fluctuations become important near t sub c because the correlation length grows large, and mean field theory becomes less accurate when long-range fluctuations dominate. And E, spontaneous symmetry breaking occurs because below T sub C, the system chooses either positive or negative magnetization, even though the Hamiltonian is symmetric from here to here. Okay, for S sub I, negative S sub I. Okay, so yeah, that's number 8. Moving along to number 9. Okay, so number 9, superconductivity problem A, B, C, and D. A, state the key experimental signatures of superconductivity. Using London theory, derive the exponential decay of magnetic field inside a superconductor. Define the London penetration depth. D, explain the physical origin of Cooper pairing with BCS theory. Distinguish between type 1 and type 2 superconductors. So this is canonical notes type stuff. Very important though. Superconductivity, key experimental signatures are rho equals 0, and the Meissner effect, meaning magnetic fields are expelled from the interior. Okay. London theory uses that J sub S equals negative N sub S E squared over M times A, and using del cross B equals U naught J and B equals del cross A. One obtains that del squared B is B over lambda sub L squared. Okay. Letter C, for a surface at x equals 0, B of x equals B of 0 e to the negative x over lambda sub L. And London penetration depth is right here. Lambda sub L equals square root of M over mu naught N sub S E squared. And D, BCS theory, electrons attract effectively through lattice vibrations. One electron distorts the lattice and another electron is attracted to that distortion. This leads to Cooper pairs. And part E right here, at type 1 superconductors here, expel magnetic field until a critical field H sub C. And type 2 superconductors have critical fields H sub C1 and H sub C2 and allow magnetic flux vertices in the mixed state. And just an addendum to this, type 2 semiconductors, they expel flux below H sub C1, then allow vortices between H sub C1 and H sub C2. Okay, so that's number 9. Let's move to number 10. Okay, so number 10 here. Okay, so number 10, consider a one-dimensional chain with nearest neighbor hopping parameter T. Here's A, B, C, D, and E. Using the type binding approximation, derive the dispersion relation E of K equals E naught minus 2T cosine Ka. Determine the bandwidth, compute the electron velocity V of K. Find the effective mass near the band minimum. Discuss how increasing orbital overlap changes the electronic properties of the material. So Tight banding approximation. A, assume the electron wave function is the sum of localized orbits, as exhibited here from psi sub k, given there. And with the nearest neighbor hopping t, E of k is this. And so we wind up with E of k is E naught minus 2t cosine of ka. Part B, the maximum energy is E sub max is E naught plus 2t. The minimum energy is E sub min equals E naught minus 2t. So the bandwidth has to be, here the W is equal to, the bandwidth is equal to 4t. C, the velocity is V of k is 1 over h bar d dk. So V of k has to equal this. Okay. And near k equals 0, cosine of ka equals 1 minus k squared a squared over 2. And E of k equals this expression here. So h bar squared over 2m star equals ta squared. We compare with E of k equals E sub min plus h bar squared k squared over 2m star. And m star just as is h bar squared over this portion here, this 2t a squared. And letter E, increasing orbital overlap increases t, which increases bandwidth and decreases effective mass. Okay, so there's a inverse correlation between the bandwidth and the effective mass there. As as you increase orbital overlap, okay, that increases t, but with the bandwidth and the effective mass, as the bandwidth increases, the mass decreases, effective mass decreases. The material becomes more conducting. Okay. Moving along to number 11. Quantum Hall effect. Derive the Landau level energies for two-dimensional electron gas in a magnetic field. That's more of a showing than anything, not deriving from scratch. Show that the degeneracy of each Landau level is proportional to magnetic flux. Part C, explain the origin of Hall conductance quantization. Part D, discuss why quantum Hall effect is extraordinarily precise experimentally. So quantum Hall effect here, for a two-dimensional electron gas and magnetic field, that omega sub c is EB over m. The Hamiltonian reduces to a harmonic oscillator form, giving Landau levels E sub n equals this. This should look familiar. H bar omega sub c of the quantity n plus 1/2, where n equals 0, 1, 2, 3, 4, on and on and on. Each Landau level has degeneracy n sub phi equals BA over the flux naught, where the flux naught equals h over e, and n sub phi. Sorry, I called it phi. Some people call it phi. My professors always called it phi. N sub phi equals EBA over h. And when Landau levels are filled, sigma sub xy equals nu e squared over h. The quantization is precise because it is topological and insensitive to many microscopic imperfections. Disorder localizes many states, allowing plateaus to form over ranges of magnetic fields. And just as a note, again, the Hall continuity is usually demonstrated as sigma sub xy equals nu e squared divided by h. And that's the setup and answers for number 11. Number 12. Okay, plasmons. Here's A, B, and C. Derive. And again, this should be more of, not derive, I should have said show. Show the bulk plasmon frequency of an electron gas. B, show the dielectric function leads to collective oscillations. And C, discuss why plasmons are longitudinal modes. So plasmons, for A, for displaced electron gas, the restoring force comes from the electric field created by charge separation. The equation of motion here is mx double dot equals negative E times capital E. A displacement x creates charge density imbalance, producing E equals NEX over epsilon naught. And therefore, mx double dot equals negative E NEX over epsilon naught. So x double dot plus NE squared over m epsilon naught x equals 0. So the plasma frequency, when we get omega by itself, omega sub p equals square root of this whole thing. Okay, so, all right, hopefully I didn't mispronounce anything so far. I probably did, but my apologies. But the math and the setups and everything are correct. Pardon my narration. Part B, the dielectric function may be written approximately as E of omega equals 1 minus this quantity here. Collective oscillations occur when E of omega equals 0. Thus, we have this relation, the omegas. And plasmons are longitudinal because the electron density oscillation produces an electric field parallel to the direction of propagation. Okay. All right. So that's 1 through 12. And hopefully I don't, and I do this all the time. A lot of times I'll mix up momentum with density and with pressure, because momentum, density, and pressure, even with the momentum, the rho to me always looks like a P. So my apologies if I ever mix up momentum, pressure, and density, because the variables to my eyes look very, very similar, and I do not have, sometimes when I'm reading so fast, I just read it as I see it, not for what the symbol actually means, and that's a flaw I have, where sometimes my mind skips. But the math is correct. Okay. All right, so 13, spin waves discuss the long wavelength dispersion relation in the ferromagnet, explain the connection between magnons and broken rotational symmetry, and discuss how magnons contribute to low temperature thermodynamics. Okay, so spin waves. So this is really interesting stuff. Textbook stuff, canonical. It's very interesting with spin waves. So for a ferromagnet, neighboring spins prefer alignment. A long wavelength disturbance slightly twists the spin direction across the lattice. For a small k, the magnon dispersion has the form omega of k is proportional to k squared for a simple isotropic ferromagnet. And more specifically, h bar omega k equals 2j s a squared k squared up to the lattice dependent numerical factors. Okay. If for letter B, magnons arise because the ordered ferromagnet breaks continuous spin rotation symmetry. The low energy excitations are smooth rotations of the order parameter. And part C in 3D, ferromagnetic magnons contribute to the lower temperature heat capacity as C sub V proportional to T to the 3 halves. And right down here, just a side note, very important, spin wave prefactor may vary by lattice. Okay, so that's this practice exam. That's if you're getting ready or if you want to just do some fun physics problems. So here are the answers and the setups. Again, I didn't do all of the computation, and again, I apologize for any miscommunication in the lighting. So I hope this could help in your studying, or if you're just practicing, having fun doing physics problems. Then thank you again, and have a good day.